at the beginning.
Okay. Hello, for who don't know me, I'm Ilaria Quaglia from Anchor, and I'm the new chair of the Climate Intervention Virtual Symposium. Today, the first speaker is Jasper de Jong, a PhD student from University of Utrecht, and his talk is going to be about the impact of sulfate aerosol geoengineering on tropical cyclones in high-resolution CSM. And yeah, he's going to present this at EGU, but maybe you want to talk more about that.
Yes. All right, I guess I'll start. Thank you very much for your introduction. Yes, so my talk indeed is about the impact of sulfate aerosol geoengineering on tropical cyclones in high-res CESM. And so here I started with a nice front cover of a lot of tropical cyclones that were present last February in the Southern Hemisphere, which is 5 at once on this photograph, and actually 6 if you include one that was there a day earlier. So that was quite unusual. I like to figure, but it's not specifically related to my research, but yeah, I guess it's very nice. Oh, wait, so I'm trying to go to the next slide, but it refuses that. Let me see what I can do. Yeah. So here's so the next slide. So when we talk about tropical cyclones, there is some research that is done on the impact of global warming. Specifically, Knudsen et al. Released a big paper in 2020 where they state that there's a global increase of tropical cyclone precipitation and intensity, and also a relative increase of the frequency of the strongest tropical cyclones, which have a category 4 or 5 on the Saffir-Simpson scale, which are very destructive tropical cyclones that can do a lot of damage. And at the same time, there's an overall decrease of the all category tropical cyclone frequencies. And they also note a poleward migration of the latitude of maximum tropical cyclone intensity in the Western North Pacific. And well, in this figure, you can also see on the right bottom plot that the global average tropical cyclone frequency decreases indeed, and it's well, there's some decrease and increase in the range of models, but the model of the category 4 to 5 frequencies, but the models that predict a decrease are usually low resolution models, and this indicates that the resolution of the models are quite important actually. But they are on the same page for intensity and rain rate estimates. So if we want to know the impact of solar geoengineering, for now we have to look at existing literature which does not use explicit tropical cyclone models, but uses semi-implicit or methods like downscaling, for example. And some studies which have combined here in this overview, they state that there is maybe some increase or decrease of the frequency, depending on where you look, but a decrease of the frequency of the strongest storms, and a decrease of the intensity, and a decrease of precipitation. So that's what we expect to find in our model. But as I said, there are no studies yet with explicit tropical cyclone tracking due to lacking resolutions. So this is a first, and we're going to present it here. So the research question is, what is the impact of delayed start SAI, which means cooling abruptly from a high forcing scenario in 2050, which we call SAI 2050, on tropical cyclones? So here's an overview of our model and experiments. We used background forcing RCP 8.5 with a CO2 equivalent method. And that starts in 2000 and is branched from equilibrated 2000 conditions. This is, of course, not exactly the reality, but we had to make this choice to save my PhD, basically, because we've tried for a very long time to get another model version running. that did use the realistic CO2 scenarios. But this, of course, is fine if you want to see what the impact is of increasing CO2 and reducing the temperature by SAI. Then our experiment SAI 2050 starts in 2050 by decreasing the temperature to 2000 values, which is just the same as the reference run from which the RCP run branched. And we use the CESM1 CON5 model, fully coupled. And note here that CON5 does not have interactive stratospheric chemistry, and I will come back to that in a second. There we have a low resolution spin-up run, which runs at 0.5 degree atmosphere and 1/10 of a degree ocean from 2000 to 2100, and the SAI run then starts at 2050, as you can see in the graph. And then from that run, we launched an ensemble of high-res members, which have a 1/4 degree atmospheric resolution and the same ocean resolution, starting in 2003 for the reference and 2093 for RCP and SAI. So they're named reference RCP 8.5 and SAI 2050. And there are a total of 6 ensemble members each, spanning 5 years. So how do we apply the aerosol forcing then if there is no interactive stratospheric chemistry? So first note why did we do it. That's because CON is about 7 times more cheaper to run than WACOM at 1 degree atmospheric resolution. Well, that was our main concern for this case because it's already quite a big simulation. So we use a feed-forward feedback controller that determines the aerosol optical depth annually. And then using predetermined fitted functions, we translate the AOD that should go into the model to the relevant forcing variables that are prescribed to CON. And for that, we must have fitted those functions before the experiment. And we used the GLENS data. I guess most of you are familiar with that. But for who's not, the GLENS project is an ensemble of members that try to keep the temperature constant at 2020 values, but also the interhemispheric and the equator to pole temperature gradient of temperatures by injecting at 4 injection locations in a specific way. And these temperature targets basically are called T0, T1, and T2 for the global mean, interhemispheric, and equator to pole gradient of temperature. So this method that we use with basically fitting those functions and translating, using them to translate the AOD is also analyzed in more depth and validated in a recently, in a preprint that we recently published. So it's on ESS Open Archive, and if you want to take a look at that, that would be great. It's still open for peer review. So now short validation. If we look at the surface temperature in this simulation, we can see that if we look, for example, at RCP 8.5 minus reference, there's a lot of warming and a lot of cooling SAI 2050, which makes it the total result SAI 2050 minus reference actually is very close to 0, especially in the tropics, and that's where it's most relevant for tropical cyclones. You can also see that on the global mean temperatures, which are shown on the bottom left, and the interhemispheric gradient and the equator to pole gradient. Also for precipitation, there is for example, southward shift of the ITCZ in the control, which is quite well reduced by SAI, and also the general pattern of precipitation change is reversed by SAI, though local changes do still exist. So it's not perfect, but especially for the temperature, we get quite good results. And well, this works well enough for tropical cyclone simulations. Then to track the tropical cyclones, we used a tracker that was made by Van Westeren et al. In 2023. And it was actually designed for this data set. They used the control data to make their own project. And it uses surface winds and 850 and 250 hectopascal winds the 850 hectopascal temperature, sea level pressure, sea surface temperature, latitude, and landmass in order to apply conditions on whether or not anomaly is detected as a tropical cyclone. And it basically follows relative vorticity maxima. So what are the results? Here we basically see what comes out of the tracker. So there's the tropical cyclone frequency, which is mainly consisting of a northern hemispheric and southern hemispheric parts, from which you can deduce the tropical cyclone season. So you can see that in the northern hemisphere, the peak of the season is about early October, and in the southern hemisphere, it's about March. And actually under RCP, there's a late start on the southern hemisphere, which is sort of reversed by doing SAI. Now we can look at the tracks, the spatial distribution of them. And well, in the reference, we still have 99 tropical cyclones per year. This is decreased to 91 in RCP 8.5 and decreased even further in SAI 2050. So that's a big decrease. And if we look at the tracks, the color means the minimum sea level pressure. So especially, for example, in the Western North Pacific, we see that in RCP 8.5, there are more strong tropical cyclones, and this is a bit diminished in SAI 2050. But overall, it looks relatively similar to the reference in SAI. Now we look at the track densities. So the track density is essentially how many tropical cyclones pass through a certain grid cell per year. And well, you can see that there are a lot of tropical cyclones in the Eastern North Pacific. And you also see, well, a lot of in the South Indian Ocean and Western North Pacific. And then in RCP 8.5, it increases in the Western North Pacific, decreases in the, before I go to the differences, these are, of course, well, runs that are not from reality. So we have 2000 conditions background. So Van Westen et al. Made a reference plot where we compared our reference with the IB tracks data set, which is a very good representation of the actual measured tropical cyclones in the world. So you can see that it overestimates the amount of tropical cyclones in the Eastern Pacific, and it underestimates those in the Western North Pacific, and also overestimates it in the South Indian Ocean. And there's also an underestimation in the North Atlantic Ocean. So, well, in RCP, we see this pattern emerge, basically, which is not there in the SAI minus reference plot. So it means that SAI is definitely opposing the changes that are happening there. But in other locations, the changes are quite similar. Look, for example, at the North Indian Ocean near India, you can see that changes are similar. Or in the Atlantic Ocean, it's also a decrease in both cases. So next slide. Then we can ask ourselves, okay, can we maybe make some distinguishment between minor and major tropical cyclones? So for this plot, I've shown the track densities for those tropical cyclones that have a maximum relative vorticity that is above the median of the value in the reference dataset. And then we can see that the high values in the East Pacific are mostly minor tropical cyclones, while the nice other patterns, like the sort of the curvature tracks that you get, because when the tropical cyclones approach land and then when they go poleward, they get carried along by the westerly, so they make sort of this curve. That's mostly the major tropical cyclones. And now we can see that those changes, that pattern that you saw on the previous slide, is mostly represented in the major tropical cyclones, and a bit, it's still in the minor, but it's definitely more, well, stronger in the major tropical cyclones. And I've also shown here some values which I will not go into detail now. So how do the tropical cyclone properties change? We can show distributions of that. So for this, here we show the sea level pressure minimum distribution for reference RCP and SAI. And on the x-axis, you see the pressure, and you see that it's not ascending, but descending. And that's so that the weaker tropical cyclones are shown on the left, basically, and stronger tropical cyclones are shown on the right. And we see that SAI mostly decreases the frequency of the very strong tropical cyclones. So with RCP, you see this increase above 940, actually below 940 hectopascals, for example, which is not that clear in SAI minus ref. And also the weaker storms, so below or above 980 hectopascal on the left side, they are reduced by SAI. So we can also do that for more variables. And the second plot, we see this plot for the maximum 10-meter winds. And we can see that while in RCP, there's a increase in the very strong winds, so above 40 meters per second. This is not clear from SCI minus ref. So SCI really tackles the large tropical cyclones indeed. And you also see that the values between 20 and 30, so the weak tropical cyclones, which are very common actually, are reduced a lot by SCI, while in between there is a lot of similarity actually, so it doesn't change that much. So you could say that SCI targets the extremes of the distributions. Then the precipitation, I think, is very clear. We see in RCP that there's an increase in very wet systems, so above 45 millimeters per hour, and a decrease in the drier systems, so below 30. And in SAI, especially this increase in the very wet storms is diminished a lot. And also there is a bit of an increase compared to RCP in the lower precipitating systems. And then I've drawn a line because the last plot is for latitude, so the left-right, weaker, stronger analogy does not hold anymore. But we see a bit of a southward shift in RCP 8.5. Oh, there was some text as well. And well, this is also kind of reduced, not present in the SCI minus ref, but we do see an overall decrease on the northern hemisphere, so there's a bit of a difference. So then we look at what may be causing this. So for that, well, I'm sorry, I forgot to mention that on the previous slide, these distributions are taken at maximum intensity, and these distributions are taken during the time until maximum intensity, which we call a development period. So we see that, for example, the sea surface temperatures are far higher in RCP than in SAI, and the wind shear we see. This is also reversed by SCI, and there are less tropical cyclones with high wind shear due to SCI. So that's what you can see, like below maybe 10 or 12 meters per second. There is not so much increase in the tropical cyclones that experience a lot of wind shear. And the last plot is for the warm core anomaly, which is a measure of the convective instability that's there for the tropical cyclones. And we see that there's a cooling shift in RCP 8.5, which is almost reversed by SCI. And the signal in SCI is now merely just a plain reduction over all values. So let's do a regional assessment. For this, I've shown a few basins on this plot. And the values that I'm going to show are presented in tables. And there are 5 variables, which are the count of tropical cyclones, which is called num. U10 is the 10-meter maximum wind. The PREC is the precipitation, shear, wind shear, and SST sea surface temperature. And so for the 10-meter winter precipitation, I've looked at values that are at maximum relative vorticity, and then the 90th percentile over all tracks. While for shear and SSTs, I have chosen to look at the development period and take the median of all tropical cyclones. And you can also see the units are on the right-hand side. So here we see all the values. So if we take a quick sort of global look, the Western North Pacific is then the only basin where SAI reverts the situation almost completely. That's what you can see with with RCP, you see a lot of bold values. So bold means that the change is significant. It's outside of the 90% confidence interval. And for RCP, you see this change everywhere, while for SAI, you don't. So it means that all this change is basically reverted by SAI. And this is not the case for all the other basins. So there's clearly a lot of change, locally. So for the total count of tropical cyclones, while SAI causes a decreased count in the northern hemisphere basins, maybe except for the North Atlantic, where SAI mitigates the decrease due to RCP 8.5 in the southern hemisphere. So you can see that there actually that SAI can be higher than the delta RCP. So in the South Pacific and the delta SAI. And the South Atlantic is, you have to be a bit cautious about interpreting that, because as you can see, there's just one tropical cyclone per year. So there are a lot of so-called significant values, but I don't think they're that significant at all. There's probably too small sample size, but I've included it just for the sake of completeness. Same holds also for the North Atlantic. There are less tropical cyclones in the North Atlantic than in other basins generally, which does have its impact on the validity of all the statistical methods. But I guess that you can get you can get the main picture from it. So you can clearly see the hemispheric difference here, where delta SAI values tend to be more negative than the delta RCP values in the northern hemisphere, while the opposite is true in the southern hemisphere. If we then look at the 10-meter wind, well, that basically increases everywhere with RCP, and SAI acts to revert this. And only in the North Atlantic, there's a bit of overcompensation. So you can see that there's just this modest increase of 1.9%, which then becomes a minus 7.8% after applying SAI. The next precipitation, this increases everywhere with RCP again, and SAI significantly reverts this. Again, there's some overcompensation in the North Atlantic, but in general, SAI does a really good job of getting the tropical cyclone precipitation states back to the reference values. If we then look at wind shear during the development period, it increases with RCP in most places, except for the North Indian Ocean, where it stays relatively the same. And SAI generally has a mitigating effect, but only mildly in the Eastern North Pacific and North Indian Ocean. And then go to SST, then we can see that, well, there's of course a lot of warming with RCP, and SAI has a cooling effect nearly everywhere. Again, there's some overcompensation in the North Atlantic. And of course, see, that was this slide. So if we look at not the regular SST, but relative surface temperature, which is defined as the surface the SST minus the global mean of the tropical mean surface temperature, then you get sort of this picture how the convective instability changes with time. And that's because the upper tropospheric temperature is highly correlated to the tropical mean surface temperature. So we can see that while control gets a lot warmer than reference, actually the relative surface temperature gets cooler. And the opposite happens in SAI. So especially in the southern hemisphere, we see that compared to control, there's a lot of warming on the southern hemisphere. And compared to reference, this leads to only very modest cooling/warming in the southern hemisphere and cooling in the northern hemisphere, which may play an important role in the hemispheric difference in impact of SEI, especially on the tropical cyclone number, where we know that SEI has a negative impact on the tropical cyclone number. Then I have some extra slides. I think there's some time for that. So if you look, for example, at the Western North Pacific.
Sorry, Jasper, you might want to wrap up if you want to have time for some questions.
Oh, sorry. Yeah, okay.
At least 20 minutes, yeah.
Oh, yeah. Yeah. So conclusions. We saw that the changes in SAI 2050 with respect to the reference for the frequency, that it decreases further than with global warming alone for all TCs. And though SAI mitigates the decrease due to global warming on the southern hemisphere, and of the strongest tropical cyclones, the frequency does not increase like in RSP 8.5. And the frequency of a weaker, more common tropical cyclone decreases. And the tropical cyclone precipitation generally does not change, which is a significant decrease compared to RSP 8.5, while global warming causes an increase of highly precipitating tropical cyclones and a decrease of weakly precipitating tropical cyclones. And SAI also reverts this. So that was my presentation. Thank you. Do you have any questions?
Thank you, Jasper. Yeah, I think we have time for one question. And okay, I don't know how to pronounce your name, Hongwei. You raise your hand. You wanna ask your question?
Yeah, this is the correct pronunciation. Thanks for the talk. Yeah, I have one question. Is like, do you have any comments on how the aerosol itself like influence the aerosol injected aerosol from SCI influence like tropical cyclones through the aerosol cloud interaction instead of like causing the, for example, the dynamic or physical process like change of ST or vertical wind shear?
Yeah. So this is not something I've looked into yet because the data is not that old. But well, of course, there is also, yeah. I guess I can't really answer that at this moment because it's probably a bit too complicated to just give my intuition.
Yeah, no worries. Maybe another quick question, like in your model, do you like inject aerosols or you just take the SI's like dynamical response to drive your model?
So we scale the aerosol field based on the temperature error that we get from a target that we set, while keeping the same distribution of the field and also the same seasonality as was found in the GLANCE data.
Got it.
So
Thanks.
the only real difference is, for example, when our models, for example, would have a large change in the climate sensitivity, for example, then you could end up with, if you have a long simulation, that at some point you need a lot more aerosols, and that would correspond to a completely different time period in the reference simulation. So that there are boundaries to how you can apply our methods. But we found that even if you completely deviate from the scenario with sort of this emergency scenario like we do now, you still get very reasonable results.
Thanks.
Okay, we don't have time for more questions, but you can still type in the chat. Just one thing before we move forward with the other speaker, can you clarify what reference is? Because I think I missed that part.
Oh, yeah.
What do you consider reference?
So
I assume it's nowadays, but yeah, go ahead.
Actually, do you mean reference in my slides or in my comments to Hongwei? Because that's
the reference scenario.
All right. So in the slides, yeah. Oh, sorry. Here in the slides, that's the reference, which is just the 2003 value out of a high resolution ensemble data.
Okay.
So
okay.
that's early century.
Okay.
Yeah.
Thank you. Okay, so we can move forward with the other speaker. Ezra, are you ready to share your screen?
Yeah, I'm ready. Yeah, and Jasper has to unshare his screen first.
Okay, in the meantime, I can introduce you. So the next speaker is Ezra Brody. He's a PhD student at Cornell University. And today he's gonna present his paper that he submitted on ESD, right?
Yeah, so I'll just go to the second slide. So this paper is currently in review. Yeah, the preprint is publicly available on EGU Sphere. I have to respond to the reviewers soon. If you reviewed this paper, thank you. I'll get back to you shortly. But yeah, so this is about using optimization tools to explore stratospheric aerosol injection strategies. So as you know, in the stratosphere, you have the Brouwer-Dobson in circulation, and this transports aerosols poleward somewhat slowly on the order of months, and east to west or west to east pretty quickly on the order of weeks. And this means that the longitude at which you inject doesn't really have an impact on the climate response, but the latitude is very important. And we see that here. These are the cooling patterns that you get from injecting aerosols at different latitudes. So as you can see, very different responses. So this suggests that, if you inject some distribution of latitudes, it results in some set of climate outcomes that's dependent on the distribution of latitudes that you injected at, which means it's impossible to analyze the results of any sort of SAI deployment simulation outside of the context of the strategy that was chosen. But this also means that the inverse is true. It means that if you want a certain set of climate outcomes, you can choose the distribution of latitudes that will most closely result in those climate outcomes. So the questions here are, what are the possibilities with this and what are the limitations? So for some motivation, SAI strategies for achieving up to 3 climate objectives simultaneously have been demonstrated in the past. That includes the T0, T1, T2 strategy that Jasper just talked about in his talk. This has been used in a lot of simulations lately. And then there's 2 more 3 objective simulations that Walkerly wrote a paper about in 2020. There's a bunch of different simulations that only control for global mean surface temperature. And then there's also some simulations that Walker ran that control for Arctic September sea ice only. But previous studies have shown that it is theoretically possible that between 6 and 8 climate objectives can be achieved simultaneously. So the question is, which 6 to 8 could theoretically be achieved simultaneously? And for ones that can't be achieved at the same time, what are the inherent trade-offs between them? So for the methodology here, I used 7 different existing simulations that span these 7 latitudes you see on the left. Since we have between 6 and 8 degrees of freedom, we chose 7 different latitudes. So the simulations that I used are the multi-objective simulation, which is the Glenn's Gauss-Arai strategy. And then I have equatorial only injection, 15 north plus 15 south injection, 30 north plus 30 south injection, and 60 north plus 60 south injection. Those 5 simulations all use a feedback controller to maintain global mean surface temperatures at approximately 1 degree above pre-industrial. And then I also have 30 north and 30 north individual and 60 north individual injection, and these are roughly constant injection, 12 teragrams per year. All of these simulations are in CESM2 WACM 6, the middle atmosphere version, with SSP2 4.5 background concentrations, and they're all from 2035 to 2069. So from here, I'm going to introduce the sort of linear quasi-static approximation I use to do the analysis. So for any climate variable y, right, y can be anything, any climate variable you care about, I'm going to define alpha as the change in that variable due to greenhouse gas forcing per 1 degree of global mean warming. The way I calculate that is I take the reference period, which is, since Solari is going to ask 2008 to 2027 in this study, and then I take a future period, 2050 to 2069, 20-year average for both of them. And there I take the difference in global mean surface temperature. This is just SSP245 scenario. And then I take the difference in whatever variable I'm looking at it. So I take the variable I'm looking at, divide by the total global mean warming, and that's how I define alpha. So it's the change in some variable per global mean warming due to greenhouse gas forcing. And then mu is the change due to SAI forcing, again, per 1 degree of global mean cooling. So I calculate that by taking, again, the 2050 to 2069 average in the SSP245 scenario, and then taking the same 2050 to 2069 average, but in an SAI simulation. And then take the difference in temperature, take the difference in whatever variable I'm looking at, and divide it by that change in temperature to get the change per degree of global mean cooling. So it's just a way of sort of picking out the forced response of variables due to greenhouse gases and due to SAI. Again, this assumes linearity. The climate system is, of course, nonlinear. It also assumes kind of a quasi-static thing where I'm just taking static averages and assuming that, I can add and subtract them. Again, the Earth is not quite quasi-static. There's all sorts of different rates of dynamics going on, particularly if you compare surface climate response to deeper ocean response. So you're probably wondering how good of an approximation this is. I did a verification that shows it is pretty good. The errors that you'll get from this linear approximation are similar or smaller than internal variability. In the interest of time, I'm going to skip that for now, but if I have time at the end, I'll go back to it, or if anyone asks about it, I'll go back to it. So that allows us to do this. So this equation on the top, so if we take, assume beta is equal to alpha plus mu, so the combined forced response to greenhouse gas changes and SAI. So if you take the 7 different ones from all 7 strategies and take some linear combination, you can approximate the forced response due to whatever strategy you want to come up with this combination of 7 latitudes. And then if you want to find the combination that best meets some objectives, you can use the equation on the bottom. So if you find some objective function j of x, you can plug all the different beta values into it and find the minimum. So for the first example of what I'm going to do with this, let's try to achieve 5 objectives simultaneously. So we're going to go with T0, T1, and T2, but also add on ITCZ and Arctic September sea ice. Now it's important to note that if you're only using 30 north, 30 south, 15 north, and 15 south, this is impossible. Walker showed that it was impossible in 2020. However, if you give yourself 7 different injection latitudes, maybe it is possible. So the mathematical way of asking this is this equation on the bottom. Is there a solution to having this objective function equal to 0, where your M objectives are T0, T1, T2, ITCZ, and SSI? And it turns out, yes, at least within limits of detectability in this study. So here you can see the responses to 4 of the 5 variables. So everything I'm doing here is normalized to 1 degree of cooling. So by definition, T0 is always set, so we don't have to look at that. But if you look at the other 4 variables, these are the responses to all of the strategies that have simulated, as well as the optimized strategy that is the solution to this optimization problem. As you can see, the purple multi-objective strategy, the one in Glenn's, does pretty well, but it doesn't quite control ITCZ within bounds of detectability. However, if you look at the optimized, which is the star on the left, it achieves all 4 objectives within bounds of detectability of the study. And if you look on the bottom right, that just shows how the distribution of latitudes is different between the multi-objective strategy and this optimal one. Now for the next problem, let's say we want to control the temperature and precipitation everywhere on Earth at the same time. So keep temperature and precipitation at reference levels everywhere. This is obviously impossible because you don't have complete control over the climate with SAI or with anything for that matter. But the question is, how close can we get? And what are the trade-offs between prioritizing temperature versus prioritizing precipitation? So the mathematical formulation's on the bottom. If we want to minimize gamma times changes in temperature plus 1 minus gamma times changes in precipitation, you'll get some answer. You'll get some strategy that does the best at this. And then as you vary gamma from 0 to 1, you'll get different strategies that prioritize temperature or precipitation more. So what that looks like is this. So if you look on the plot on the left, each of the colored dots are the simulated strategies. The black colored dot is just no SAI, just SSP245 in the future. And if you look at the square, all of those black squares are the solutions to the optimization problem with different values of gamma ranging from 0 to 1. So they make a Pareto front, and these are sort of the optimal SAI strategies for minimizing RMS temperature precipitation, depending on how much you care about each of them. So the question there is, okay, clearly the Pareto front is doing better than any of the individual strategies, but the question is, how significant are these differences given the sources of error in the study as well as just natural variability? So that's what I tried to pick out with this graph on the right. It's the same thing, but the big circles are ensemble averages and the small circles are individual ensemble members. So if you look at sort of the spread between the small circles of the same color, that gives you an idea of internal variability. So if you compare the sort of how far away circles of the same color are versus, let's say, how far away the big purple circle is from that corner of the Pareto front that's closest to it, they're pretty similar. And that would suggest that the difference between the multi-objective strategy and the optimal temperature strategy is not really detectable in this study and maybe not significant compared to internal variability. However, if you look at, say, the purple dot, the multi-objective strategy, versus the bottom right corner of the Pareto front, which is the optimal precipitation strategy, you can say that those probably are significantly different. And the other thing to note is the purple square on the right figure, that is the value of the multi-objective strategy using the linear quasi-static approximation model that we have here. So if you can look at sort of the distance between the little purple square and the big purple circle, that sort of gives you an idea of the magnitude of the error due to the linear approximation I'm using here. And this is, I guess, more of a visualization of what these patterns look like in the different optimal strategies. The top row is the optimal temperature strategy, the bottom row is the optimal precipitation strategy, and the one in the middle is a balanced strategy that weights temperature and precipitation evenly. You can see there are some differences. Main difference here is that as you prioritize precipitation more, you end up doing more SAI closer to the poles, which doesn't affect the precipitation as much. And then you get overcooling towards the poles, undercooling towards the tropics. So this is sort of what the injection rates look like in the different strategies along the Pareto front. For me, the most interesting thing here is that the equator is so largely used, even though we all know that injecting at the equator gives like a very strong concentration of aerosols and thus AOD very close to the equator, which I mean, most modelers or most people who run SAI simulations have been trying to avoid that, which is why most simulations use 15 and 30 degrees. But yeah, I just thought it was interesting that it uses so much of equatorial injection. And then I thought, okay, maybe you don't care about global temperature and precipitation changes that much. Maybe what you really care about is how much does temperature over land and precipitation minus evaporation over land change. So if I optimize for minimizing those changes, does it look any different? And yeah, it looks somewhat different, but again, it's a similar story, or the multi-objective strategy, the purple dot, is already very similar to the optimal temperature strategy, and you can't really tell a difference in the study. But again, precipitation strategy is probably significantly different. And if you look at the patterns on the left, they do appear to be very, very similar to the patterns for just optimizing for global land temperature and precipitation rather than land only. Yeah, I don't have them next to each other, but they're pretty similar. And again, here's how the injection rates change as you prioritize land temperature and land precipitation minus evaporation. This uses a more even distribution of latitudes than the global strategy. But as I said before, the resulting pattern isn't all that different, even though the injection distribution is pretty different. So now, as I was saying earlier, the global temperature versus precipitation strategy used a lot of equatorial injection. So I thought to myself, okay, what happens if I say it's not allowed to use the equator? What happens? And that's what you get on the left, the result of the optimization without the equator. And as you can see, it more or less just replaces the equator with a combination of 15 degrees north and south. And in doing so, you actually need about 3 teragrams per year less of total injection, as you can see with the black line on top. And then the question is, how much worse is that from a climate standpoint? So the Pareto front with the stars now is the one without the equator. The one with the squares is the one with the equator allowed, like earlier. And as you can see, the distance between these two Pareto fronts is very small compared to both internal variability and the potential error due to the linear approximation I used. So yeah, that's all I have in conclusion. It is possible to manage more than 3 climate goals simultaneously. It's not possible to manage everything simultaneously, and thus there are inherent trade-offs between certain variables. There are likely strategies that can do better than any strategy we've tried so far. However, it's hard to say really how significant the improvement is with the data that I have available to me and the methods that I used. And the other thing is that all the simulations I've used, and since my model is linear, it really is only relevant to when you're talking about approximately 1 degree of global mean cooling. It'll take a long time to get to a whole degree of global mean cooling. In the first few decades, when there's way less, any forced response will be much smaller compared to internal variability, so it will be less important, but also harder to detect, harder to really figure out how much of a result the strategy it is. So yeah, so nothing about this study really affects early deployment considerations. How am I doing on time?
Yes. Do you have
Yes, like
anything else you want to show?
that was exactly 20 minutes, or?
Yeah, it was exactly. Good job.
Oh, wow. That was lucky. All right. Yeah. So I guess I'll open it up to questions. And if anyone wants to see the verification of the linear approximation, I can show that as well.
Yes. Can I start with a question? Because I don't see any question on the chat. Oh, there is a hand raised.
There's at least 2 hands raised.
Okay. Then how can I find who is the one who wants to ask question?
I've seen Simona and Matthew. I don't know if there were other hands raised as well.
Okay, then let's start with Simone while I figure out how to.
Hi, thanks. Very nice talk. I don't know. I see the hand raise when you click on the participants, maybe. I don't know if you can see that. Anyways, very nice talk, and I haven't seen it. So maybe you can go back a couple slides. And this, for example, the other one back or forward. The one where you have the dots, not this one, but the other one with the dots in the slide, this, for example. So what I'm seeing, or if I understand it right, you have the multiple injection strategies. That's the purple, multiple objectives, which is your 5 objectives, right?
No. This purple, this is the T0, T1, and T2 strategy. This is the Glenn's strategy.
I see. And that one is closer to, more closer to optimizing temperature, obviously. And since
Yeah.
you're using CSM2, you do not get the precipitation quite great, right? Because we're shifting somewhat the ITCZ.
Yeah, I mean,
Right.
the multi-objective strategy attempts to control that with the T1, but you know, it doesn't do a great job, and the tropical precipitation still shifts a decent amount. Yeah.
Okay, so I guess the black dots or squares are including your multiple strategies, is what you're saying.
So the black square, the black squares are the strategies that attempt to optimize for difference in temperature and precipitation. It's different than the 5 objective strategy.
Okay, where's the 5 objectives?
Okay, so if I go back, I don't have it here, but here it is. Okay, so on this one on the right, the gray square is the 5 objective strategy.
Okay, so why is that actually much closer to the multiple objective? You would think that the 5 objective would have also would be more to the optimized black points, right? Or would you not?
So the black squares are optimizing for global RMS temperature and precipitation change, whereas the gray square optimizes for T0, T1, T2, ITCZ, and September sea ice. So they're different objectives, and they end up manifesting somewhat differently.
Okay, so since you're actually sea ice is something that will be more like temperature control, you'll be more in the temperature control area. Is that how you can understand? If you would choose something that's more precipitation related, you may get more into the precipitation optimizing.
Yeah, so I mean, September sea ice is due to temperature, but only in a very small part of the world. So if you're looking at global changes in temperature, it's only a little bit of a difference. I mean, what we see is that the strategies that do better in precipitation do more towards the poles. But also, I mean, maybe a slightly different hemispheric balance just because the CESM is, you know, I guess a little weird with with the hemispheric balance.
Okay, well, thanks for explaining. I had many questions, but that helps a lot. Thank you.
Yeah, sorry, it's complicated, and I definitely didn't do a very thorough job of explaining.
Oh, no, it's
what's going on
just
here.
complicated. Yeah, and that's all. Thank you.
Okay, Mike has a question. Mike, go ahead.
Thank you. I'm wondering if you can also optimize with respect to special features that matter to people, like strength of the monsoons or occurrence of, you know, extremely hot summers or amount of warming over Greenland or something. So do you have a real broad choice of possible features that you could optimize with respect to?
Yeah, so with the method I have here, I can optimize for literally anything that is an output variable in CESM. The only implications are, well, one is I deliberately kind of chose broad, large scale things because I didn't, I sort of wanted to not quite get into impact with this paper, just keep it more broad. But also, I think the smaller scale, both spatially and temporal, that you get into, maybe the harder it is to pick out significant responses in the climate model, but maybe also the harder it is to be sure that your climate model is doing things correctly. But yes, that's absolutely, I think, you know, like all the objectives that I chose in this talk are not really super significant for people. They're just kind of broad climate things.
Yeah, I was sort of asking because this notion of countries getting interested in it has to do with generally features that might really affect them or drive them to something. So interesting.
Yeah, and again, the linearity test I did it for temperature and precipitation kind of globally. I didn't do it for finer features, so I'm not sure if it would hold up.
Okay, next question is from Andrew.
Yeah, could you explain the diagram where you had the two vectors that came almost back to the origin? Because I thought that was temperature and precipitation, but it wasn't. But I really just
This
didn't
one?
understand. Yeah.
So y is just any variable. It can be precipitation, it can be temperature. On the x-axis, that's just global mean temperature. So say as you let carbon dioxide warm the climate by 1 degree, all of your other variables will change by some amount. And that some amount I'm defining as alpha. And then if you also, if you use SAI to cool by, again, 1 degree to try to keep temperatures the same as the reference climate, your variables will change again, but they won't change necessarily the exact same as the opposite of the change due to warming. So you'll get, that's why, you don't get the exact same, if you do SAI, you can't perfectly keep the climate at the reference period because things change differently with respect to greenhouse gases and with SAI, even with the same amount of global warming and cooling. Does that make sense?
I assume it does. Okay, we have 2 minutes left. I don't see any other question.
No,
So
Matthew had a question earlier. I don't know if he still has a question.
I was just
I
clapping,
don't see.
actually.
Yeah,
But
that's why I was
hands up,
confused
it's,
about.
So yeah, I'm good.
All right, yeah.
Okay.
Thanks for listening. If you have any questions, you can feel free to why is this not working? Well, I was going to say you can feel free to ask me. You can feel free to email me. I was going to show my email, but my slideshow. Oh, okay. Yeah, you can feel free to ask me. Also, if you're going to be in Cape Town in a few weeks, you can ask me there.
Okay. So thank you, Ezra. Thank you, Jasper. And we will see in a month. Bye.